In the deepest reaches of space, where light takes billions of years to reach us, where galaxies swirl like storms frozen in time, something happened. Something brief, something violent, something beautiful. It lasted only a few seconds. A flash faint at first, then glowing with a strange, silvery fire. Not the blue-white fury of a supernova, not the steady burn of a star, but something different. A light that pulsed with the weight of creation itself. And when it faded, the universe was changed. Not in a way anyone could see with their eyes, not in a way that shook planets or shattered worlds, but in a way that seeded the cosmos with something rare, something precious, something golden. This was no ordinary explosion. This was a kilonova. The name sounds small. Kilo means 1,000. But this event wasn't small. It was one of the most powerful explosions in the universe, just not in the way we usually think. No, a kilonova doesn't shine by burning fuel like a star. It doesn't collapse under gravity like a supernova. A kilonova is born from collision, from the final desperate embrace of two dead stars, neutron stars, spiraling toward each other at nearly the speed of light. Pulled by gravity so intense it warps the very fabric of space and time. And when they meet, they don't just explode. They transform. For a fleeting moment, the laws of physics are stretched to their limit. Matter is squeezed beyond comprehension. Neutrons are flung outward at incredible speeds. And in that chaos, in that unimaginable heat and pressure, something miraculous happens. New elements are born. Elements that didn't exist before. Elements like gold. Yes, gold. The same gold that gleams in jewelry, that fills vaults, that has driven empires to war and explorers to sail unknown oceans. That gold, every ounce of it, was forged in events like this. Not in the hearts of living stars, not in the quiet fusion of hydrogen into helium, but in the violent death spiral of two of the densest objects in the universe. A kilonova isn't just an explosion, it's a cosmic forge, and we are only now beginning to understand it. Imagine, for a moment, the scene. Two city-sized stars, each more massive than our sun, yet crushed into a sphere only 20 kilometers across. A single teaspoon of their material would weigh 1 billion tons. They orbit each other, faster and faster, closer and closer, like dancers locked in a fatal waltz. Their gravity distorts space around them, sending ripples outward. Ripples Einstein predicted over a century ago, called gravitational waves. These waves travel across the universe at the speed of light, invisible, silent, but carrying the signature of catastrophe. And then impact. In less than a second, the stars merge. The collision is so violent, it briefly outshines entire galaxies in gamma rays. A jet of energy blasts into space. The outer layers are torn apart, flung into the void, glowing with radioactive light. This is the kilonova. And in that glowing debris, atoms are being stitched together, neutron by neutron, building elements heavier than anything nature usually allows. For most of human history, we had no idea where gold came from. We dug it from the earth, marveled at its luster, worshipped it as divine. Alchemists dreamed of turning lead into gold, not knowing that the universe had already solved the puzzle through violence, through gravity, through the death of stars. It wasn't until the 20th century that we began to understand stellar fusion, the process by which stars cook hydrogen into helium, then helium into carbon, oxygen, and up to iron. But iron is where fusion stops. Beyond iron, you can't get energy from fusion. To make heavier elements, like silver, platinum, uranium, and yes, gold, you need something else. You need an environment where neutrons flood atomic nuclei faster than they can decay. You need the rapid neutron capture process, the R process. And for decades, scientists debated, where does the R process happen? Supernovae? Maybe. But the conditions weren't quite right. There wasn't enough neutron-rich material. The temperatures and densities weren't extreme enough. The puzzle remained unsolved until the stars themselves sent us a message. On August 17, 2017, that message arrived. It began with a whisper, a tiny vibration in space-time detected by two giant L-shaped machines buried beneath the Earth in the United States. Then, 2 seconds later, a satellite in orbit caught a burst of gamma rays from the same direction. Telescopes around the world swiveled toward a single point in the sky, in the constellation Hydra. And there it was, a new point of light, fading over days, glowing with the unmistakable signature of a kilonova. For the first time in history, humanity had witnessed the collision of two neutron stars and the birth of heavy elements in real time. The data poured in. The spectra showed the fingerprints of strontium, cesium, iodine, and gold. Not just traces. Hundreds of Earth masses worth of gold, created in seconds, scattered into space, drifting even now through the galaxy. This wasn't just a discovery, it was a revelation. It changed how we see the universe. It changed how we see ourselves. Because if all the gold on Earth came from such collisions, then every wedding ring, every ancient coin, every artifact of human civilization made of gold has its origin in a cosmic catastrophe that happened billions of years ago in a distant galaxy, long before our sun was born. We are not just made of stardust, we are made of star wreckage, of neutron star ash, of gold forged in fire and chaos. And yet, most people have never heard of a kilonova. We know supernovae, we know black holes, we know quasars and pulsars and even magnetars. Those ultramagnetic neutron stars that can erase credit cards from halfway across the galaxy. But Kilonovae? They're still in the shadows. Not because they're unimportant, quite the opposite. They may be the reason we exist. Without them, the universe would be poorer. Literally, no gold, no platinum, no uranium, no iodine in our medicine, no cesium in our atomic clocks. The periodic table would be incomplete. Life as we know it might not have the chemical diversity it needs to arise. The kilonova is not just a spectacle, it's a creator, a sculptor of matter, a hidden architect of complexity. So why haven't we heard more about it? Perhaps because it's so recent. The first confirmed kilonova was observed just a few years ago, perhaps because it's so rare. These collisions happen only once every 10,000 to 100,000 years in a galaxy like ours. Too infrequent for ancient astronomers to witness, too faint for early telescopes to catch. Or perhaps it's because the story is so hard to believe. Two dead stars, spinning around each other for millions of years, slowly losing energy to gravitational waves, spiraling inward like water down a drain. Until, in a fraction of a second, they merge and explode, creating gold in the process. It sounds like science fiction, but it's not. It's science fact, and it's one of the most profound discoveries of our time. Now, imagine standing on a planet orbiting a star in a distant galaxy. You look up at the night sky. You see the familiar constellations, the slow drift of stars. And then, without warning, a new star appears. Not bright like a supernova, but steady, glowing with a pale, opalescent light. It grows brighter over hours, then slowly fades over days. You don't know it, but what you're seeing is the aftermath of a kilonova. The debris from two neutron stars is expanding, cooling, radiating away the energy of creation. And within that glowing cloud, atoms are forming. Gold atoms, platinum atoms, rare earth elements, each one a tiny monument to the violence that birthed them. Over millions of years, that cloud will mix with interstellar gas, collapse into new stars, form new planets, and on one of those planets, life may arise. And one day, a species may dig into the ground and find gold. And they will marvel at its beauty. They will trade it, fight over it, wear it as a symbol of love. But they will never know unless someone tells them that their gold was born in a collision of dead stars, in a flash of light across the universe. That's the story we're about to tell. Not just the science, though we'll dive deep into that, but the meaning, the wonder, the connection between the cosmos and the ring on your finger. This is the story of the Kilonova, of how gold was born in a cosmic collision, of how the universe, in its most violent moments, creates the most beautiful things, of how we are all, in a very real sense, children of star crashes. So take a breath. Let the silence of space surround you. Look up and prepare to witness one of the most extraordinary events in the universe, not with your eyes, but with your imagination. Because what we're about to explore isn't just astronomy, it's alchemy, it's poetry, it's the origin of treasure. And it all begins with a whisper in space-time. It began with a ripple, not in water, not in air, but in the very fabric of reality, a distortion so subtle, so delicate, that it took a century of human ingenuity just to detect it. On the morning of August 17, 2017, at 8:41 and 4 seconds Eastern Daylight Time, two identical instruments, L-shaped vacuum chambers stretching 4 kilometers across the quiet forests of Hanford, Washington, and Livingston, Louisiana, recorded a tiny, rhythmic stretching and squeezing of space itself. The signal lasted just over a minute. It started low, like a deep cello note, then rose in pitch and intensity, faster and faster, until it ended in a sudden chirp. It was the sound of space-time vibrating, the sound of two stars dying. This was gravitational wave signal, GW170817, the first ever detection of colliding neutron stars. But no one knew that yet, not immediately. The computers at the Laser Interferometer Gravitational Wave Observatory, LIGO, flagged the event as significant, strong, clean, unmistakable. And unlike any previous detection, the earlier gravitational wave events had come from black holes, merging dark, invisible objects that leave no light behind. But this signal was different. It lasted longer. The masses were smaller. And the waveform suggested something new. Two ultra-dense objects, each about 1.1 to 1.6 times the mass of our Sun, spiraling together in a final fatal embrace. Neutron stars. At the same moment, well, almost, the Fermi Gamma Ray Space Telescope, orbiting high above Earth, detected a short burst of gamma rays. Just 1 second after the gravitational wave signal ended, a pulse of high-energy light flashed across space and struck Fermi's sensors. It lasted only 2 seconds. Short, sharp, precise, and coming from the same region of the sky. The odds of this being a coincidence? Astronomers calculated it at less than 1 in a million. This was no accident. This was connection. This was the universe speaking in two languages at once, gravity and light. The alert went out. Within minutes, emails, texts, and automated notifications flooded observatories across the globe. Possible neutron star merger. Follow-up requested. Telescopes on mountains, in deserts, in orbit, swiveled toward the patch of sky where the signal originated. The coordinates were broad about 30 square degrees, roughly the size of 150 full moons. But in astronomy, that was a bullseye. Teams scrambled, cameras turned, domes opened, and then, less than 11 hours after the gravitational wave hit Earth, the Swope telescope in Chile found it. A new point of light in the outer arms of a galaxy called NGC 4993, located about 1,000 million light-years away. Faint, blue at first, then shifting to red over the following days. Not a supernova, not a flare. This was something new. This was a kilonova. The world of astronomy had just changed forever. For the first time in history, humanity had observed a cataclysmic cosmic event through both gravitational waves and electromagnetic radiation, light across the spectrum. This was multi-messenger astronomy in action, not just seeing the universe, not just hearing it, but feeling it in the stretching of space-time itself. It was like being born blind and suddenly gaining not only sight, but hearing, touch, and intuition, all at once. We weren't just observing the cosmos anymore. We were experiencing it. The data poured in. Within days, over 70 observatories on 5 continents and in space had trained their instruments on NGC 4993. Optical telescopes captured the fading glow. Infrared detectors measured the heat of radioactive decay. X-ray and radio telescopes waited for the afterglow, the lingering echo of a jet of material moving at near light speed. Every wavelength told a part of the story, and slowly, like pieces of a shattered mirror being reassembled, the full picture emerged. What they saw confirmed decades of theory. The blue light in the first hours came from lighter elements. Strontium, calcium, cesium formed in the outer, faster ejecta of the explosion. As the debris expanded and cooled, heavier elements took over. The glow turned red, dominated by the radioactive decay of newly forged atoms. Elements forged in conditions so extreme they can't exist on Earth. This was the R process in real time. The universe wasn't just theorizing heavy element creation. It was showing us. And then came the numbers. Calculations based on the light output, the expansion speed, the spectra, all pointed to something staggering. In that single fleeting event, the Kilonova produced an amount of gold equivalent to between 3 and 13 times the mass of Earth. Not grams, not kilograms. Earth masses. That's enough gold to fill billions of Olympic-sized swimming pools. And that was just gold. Add in platinum, uranium, silver, and other rare elements, and the total mass of heavy elements created in seconds was mind-boggling. All of it flung into space at thousands of kilometers per second, destined to drift through the galaxy, eventually becoming part of new stars, new planets, new worlds. Think about that. All the gold in Earth's crust, estimated at around 2.5 billion metric tons, could have come from just a handful of such collisions over the past few billion years. Some may have happened before the sun was born. Their debris mixed into the giant molecular cloud that collapsed to form our solar system. When Earth formed, that gold sank into the core, but some was left behind in the mantle and crust, brought to the surface by volcanic activity and asteroid impacts. The gold we mine today, it's not terrestrial, it's extraterrestrial. It's stardust from a collision that happened long before life existed, and we saw it happen. The significance of GW170817 cannot be overstated. Before this event, Kilonovae were theoretical, predicted by models, suggested by indirect evidence, but never confirmed. Some scientists even doubted they existed. Now, not only were they real, but they were proven to be the primary source of the heaviest elements in the universe. The single detection rewrote textbooks. It confirmed Einstein's theory of general relativity in a new regime. It proved that short gamma-ray bursts are caused by neutron star mergers. It gave us a new way to measure the expansion of the universe. And it answered a question that had puzzled humanity for millennia. Where does gold come from? But let's step back for a moment. Let's feel the human side of this discovery. Imagine being one of the scientists at LIGO when the signal came in. You've spent your life building machines so sensitive they can detect a change in distance smaller than 1/10,000th the width of a proton. You've waited years for a signal, and then, there it is, clear, strong, and not from black holes, from neutron stars, and then gamma rays, and then light. You realize you're witnessing something no human has ever seen before. You're the first eyes on a cosmic event, 130 million light years away. You're listening to the death scream of two stars and watching the birth of gold. You're not just observing science, you're making it. After decades of searching, modeling, doubting, hoping, there it was. Proof, connection, understanding. It was like finding a missing page in the story of the universe. And the public, they noticed too. News outlets around the world ran headlines. Scientists witnessed birth of gold in space. Cosmic collision creates heavy elements. We are made of star stuff, literally. For a brief moment, the world paused to marvel at the cosmos, at the idea that the universe isn't just vast and cold, but creative, generous. That in its most violent acts, it produces beauty. That the gold in a wedding ring has a story written in gravity waves and gamma rays. But here's the most astonishing part. This event wasn't unique. It was just the first one we caught. There are likely thousands of neutron star mergers happening across the universe every year. We just haven't seen them yet. With more sensitive detectors, better coordination, and faster response times, we'll witness more Kilonovae in the coming decades. Each one will teach us more about the equation of state of neutron stars, about the behavior of matter at nuclear density, about the origin of magnetic fields, about the formation of black holes, and each one will scatter more heavy elements into space, seeding the galaxy with the building blocks of planets and life. What's more, GW170817 helped solve a long-standing mystery, the origin of short gamma-ray bursts. For years, astronomers had observed these intense flashes of gamma rays lasting less than 2 seconds, but they didn't know what caused them. The leading theory was neutron star mergers. GW170817 confirmed it. The 2-second gamma-ray burst detected by Fermi was the jet of energy fired out from the collision, aimed almost directly at Earth, but not quite. If it had been pointed straight at us, it might have been dangerous. As it was a lucky glance, a cosmic lighthouse sweeping past our planet. And the afterglow? It took days to appear. X-ray and radio emissions were detected weeks later, caused by the jet slamming into surrounding gas. This helped confirm that neutron star mergers don't just produce a spherical explosion, they also launch focused beams of energy, like cosmic blowtorches. These jets may be how some of the most energetic events in the universe begin. Even the gravitational wave signal itself held secrets. The way the waveform evolved told scientists about the star's masses, their spins, their tidal deformation. the way they stretched each other before merging. From this, researchers could infer properties of neutron star matter, how stiff it is, how it resists collapse. This is information you can't get in any lab on Earth. You need a collision of neutron stars to probe matter at this density. In the month that followed, paper after paper was published. Over 100 scientific studies emerged from a single event. Conferences buzzed with excitement. Students changed their research topics. New collaborations formed. GW170817 wasn't just a discovery. It was a revolution. And yet, for all the data, the equations, the telescopes, the supercomputers, the most powerful tool in this discovery was curiosity, human curiosity. The desire to know where we come from, what the universe is made of, why things are the way they are. That curiosity built LIGO. That curiosity launched Fermi. That curiosity drove astronomers to stay up all night, scanning the skies for a faint dot of light. And that curiosity is what drives you to watch this video. Because you want to understand, not just the facts, but the meaning, the wonder, the connection between a flash in a distant galaxy and the gold resting on your skin. That's what this journey is about. And we're just getting started. Now that we've seen the discovery, we need to go deeper. We need to understand what collided. Not just neutron stars, but what they are. What makes them so extreme? How they live, how they die, and how they end up in a death spiral that creates gold. So let's turn our gaze back to the stars themselves. Let's return to the beginning of their story. Because to understand the Kilonova, we must first understand the dancers in this final waltz. Before there was fire, before there was gold, before there was light, there were two stars. Not ordinary stars, not like our sun, gently burning hydrogen in a stable fusion furnace. These were massive, brilliant, violent stars, giants that lived fast and died young. Stars born from vast clouds of gas and dust. Stars that burned through their fuel in just a few million years, mere blinks in cosmic time. They lived, they burned, they exploded. And from their ashes, something even more extreme was born, neutron stars. To understand the Kilonova, we must first understand these stellar ghosts. Because the Kilonova doesn't happen with just any stars. It requires two of the most extreme objects in the universe. Neutron stars spiraling together in a cosmic death dance that can last millions of years before ending in a flash that lasts less than a second. So what is a neutron star? Imagine taking the entire mass of our some 330,000 times the mass of Earth, and crushing it into a sphere no wider than a city, 20 kilometers across, smaller than many metropolitan areas. Now imagine standing on its surface. The gravity would be so intense that if you jumped, you'd hit the ground again at nearly a third the speed of light. A single sugar cube-sized piece of this material would weigh as much as a mountain. Over 1 billion tons. This is not science fiction. This is reality. This is a neutron star. It forms in the aftermath of a supernova, the explosive death of a massive star. When such a star runs out of fuel, it can no longer support itself against its own gravity. The core collapses in on itself at speeds up to 70,000 kilometers per second. In less than a second, the core implodes. Electrons are forced into protons, creating neutrons and neutrinos in a process called neutronization. The outer layers of the star rebound off the ultra-dense core and explode outward in a supernova blast visible across galaxies. But at the center, a ball of pure neutrons remains, held up not by fusion, not by heat, but by neutron degeneracy pressure. A quantum mechanical force that prevents matter from collapsing further. This is a neutron star. It is the densest form of matter we can observe directly. Not a black hole, not a quark star, though we'll get to those. A neutron star is matter pushed to the edge of physical possibility. Its surface is a crust of iron nuclei and electrons, compressed into a lattice harder than any known material. Beneath it, the density increases so much that atoms dissolve. Protons and electrons vanish. Only neutrons remain, packed together like marbles in a box, but under such pressure that they begin to overlap, forming exotic states of matter we can't replicate on Earth. Some models suggest the core may contain superfluid neutrons, a frictionless liquid that flows without resistance, or even hyperons, strange particles that only exist under extreme conditions. We don't know for sure. No lab on Earth can simulate this. Only the universe can. And yet, for all its density, a neutron star is also incredibly dynamic. Most spin rapidly, some hundreds of times per second. The fastest known neutron star, PSRJ 1748-22446 AD, spins 716 times every second. That's faster than a kitchen blender. At the equator, the surface is moving at about 24% the speed of light. If you could stand on it and survive the gravity and radiation, you'd be flung into space in less than a millisecond. These spinning neutron stars emit beams of radiation from their magnetic poles. If those beams sweep past Earth, we detect them as pulses, hence the name pulsar. It's like a cosmic lighthouse, flashing with perfect regularity. But not all neutron stars are pulsars. Some are quiet, some are hidden, and some, like the pair that created GW7U817T, exist in binary systems. Two stars born together, living together, dying together. And in rare cases, both stars go supernova, each leaving behind a neutron star. Now, instead of one dead star, there are two. And if they're close enough, gravity takes over. They begin to orbit each other. Not in a wide, lazy loop, but in a tight, decaying spiral. And here's where Einstein comes in again. According to general relativity, any two massive objects orbiting each other will lose energy by radiating gravitational waves, ripples in space-time. It's like two ice skaters holding hands and spinning. As they pull closer, they spin faster, but they also lose energy to friction. In space, there's no friction, but there is gravitational radiation, and over millions of years, those tiny energy losses add up. The orbit shrinks, the stars move faster, the gravitational waves grow stronger, the spiral tightens, and the dance accelerates. This phase can last hundreds of millions of years. The two neutron stars may have orbited each other since before complex life existed on Earth. They've outlasted continents, ice ages, extinctions. But now, in the final minutes, the pace becomes frantic. In the last minute before collision, they complete thousands of orbits. Their surfaces stretch toward each other, deformed by tidal forces so strong they rival the gravity at the event horizon of a black hole. Neutron-rich material begins to peel off, forming a tenuous stream between them. The space around them vibrates with gravitational waves, increasing in frequency and amplitude, the chirp that LIGO detected, and then impact. But even before that moment, the conditions are already extreme. The magnetic fields of neutron stars are trillions of times stronger than Earth's. When two such stars approach, their magnetospheres interact violently, generating electric currents and particle acceleration. Some models suggest that even before the merger, the system can emit bursts of gamma rays or X-rays precursors to the main event. But the real drama begins at the moment of contact. When the two stars finally touch, it's not like two balls colliding. It's more like two droplets of liquid merging, except this liquid is denser than an atomic nucleus and spinning at a significant fraction of light speed. The collision is so violent that it briefly forms a single hypermassive object, either an even denser neutron star or, more likely, a black hole. For a few milliseconds, this object may resist collapse, held up by rapid rotation and thermal pressure. It spins wildly, distorting into an ellipsoid, flinging out streams of neutron-rich matter at speeds up to 30% the speed of light. This ejected material is the seed of the kilonova. Meanwhile, the intense heat of the collision, reaching hundreds of billions of degrees Kelvin, creates a fireball of radiation. Neutrinos flood out, carrying away energy. Magnetic fields twist into knots, launching a relativistic jet, a narrow beam of particles moving at nearly light speed. If this jet is pointed even slightly toward Earth, we detect it as a short gamma-ray burst. The entire event releases more energy in seconds than our Sun will emit in its entire 10 billion-year lifetime. But here's the key. Unlike a supernova, which produces elements up to iron, the neutron-star merger creates conditions perfect for the R process, the rapid neutron capture process. In the ejected debris, free neutrons bombard atomic nuclei at such high rates that they build up into heavy elements before the nuclei have time to decay. This is how gold, platinum, uranium, and other rare elements are formed. Not slowly, over time, but explosively, in seconds. And all of this, the gravitational waves, the gamma rays, the ejection of matter, the formation of heavy elements, depends on the properties of the neutron. Stars themselves, their masses, their spins, their equation of state, how matter behaves at such extreme densities. Even small differences in these properties can change the outcome, whether a black hole forms immediately or a short-lived neutron star, whether the jet is strong or weak, how much gold is produced. That's why studying neutron stars is so crucial. They're not just cosmic oddities, they're laboratories of extreme physics. By observing their mergers, we're probing the behavior of matter under conditions that cannot be recreated on Earth. We're testing the limits of nuclear physics, general relativity, and quantum mechanics, all at once. And yet, despite how much we've learned, neutron stars remain deeply mysterious. What exactly is their internal structure? Do they have solid crusts, liquid interiors, a core of quark matter? Some theories suggest that under such pressure, neutrons might break down into their constituent quarks, forming a quark star, a hypothetical object even denser than a neutron star. We don't know. No observation has confirmed it yet. But in the violent chaos of a Kilonova, such states might briefly exist before collapsing into a black hole. Another mystery, magnetars. Some neutron stars have magnetic fields so strong they can rip apart atoms from thousands of kilometers away. These are magnetars. Could a kilonova produce a magnetar? Possibly. If the merged object spins rapidly and has intense internal dynamos, it might generate a magnetic field trillions of times stronger than Earth's. Such an object could power a longer-lasting kilonova, glowing for weeks instead of days. Some observed kilonovae show exactly that, extended emission that can't be explained by radioactive decay alone. This suggests that a newborn magnetar might be feeding energy into the explosion, like a cosmic battery. So the neutron stars aren't just passive participants in this event. They are active agents, shaping the explosion, determining what elements are made, influencing whether a jet forms, how much matter is ejected, how bright the kilonova shines. They are not just the fuel for the kilonova. They are the kilonova. And their story begins long before the collision. It begins in the birth of massive stars, in supernova explosions, in the slow, inevitable spiral dictated by gravity and relativity. They are the survivors of stellar death, the remnants of cosmic violence, and in their final moments they become creators. But to truly appreciate the kilonova, we must witness the collision itself, not just the build-up, not just the aftermath, but the moment when two stars become one, when space-time trembles, when matter is torn apart, when gold is born. That moment, fractions of a second long, yet universe-altering, is what we'll explore next. Because in the heart of the kilonova, in the instant of impact, the universe reveals its most extreme physics and its most beautiful alchemy. It happens in less than a second, a time scale so brief that human perception cannot grasp it. A heartbeat is about a third of a second, a blink of the eye, 3/10 of a second. But this event, the merger of two neutron stars, unfolds in milliseconds. And yet, in that vanishingly short span, the universe performs one of its most extreme acts of creation and destruction. This is not just a collision, it is a transformation, a metamorphosis of matter, energy, gravity, and space-time. This is the moment when two dead stars cease to exist, and something entirely new is born. Imagine the final orbit. The two neutron stars, each about 20 kilometers wide, spinning around each other hundreds of times per second. Their surfaces are deformed by tidal forces so strong they stretch the stars into egg-like shapes. Space itself is twisting around them, dragged by their immense gravity and rapid rotation. Gravitational waves flood outward, carrying away energy, tightening the spiral. The frequency of the waves rises, the chirp until it peaks at over 1,000 hertz. And then, contact. The first point of impact is not a gentle touch. It is a cataclysm. At the moment the surfaces meet, the relative speed is nearly 1/3 the speed of light, around 100,000 kilometers per second. There is no cushion, no atmosphere to slow them down. Just pure, degenerate neutron matter slamming into itself with unimaginable force. The collision is so violent that it doesn't just merge the stars, it shatters them. For a fraction of a second, just 10 to 20 milliseconds, the two stars don't fully coalesce. Instead, they bounce. Like two water droplets colliding in slow motion, they deform, stretch, and briefly rebound. But gravity is too strong. The rebound fails. They collapse back together, forming a single hypermassive object at the center. This new object is briefly more massive than any stable neutron star can be, perhaps 2.7 to 2.8 times the mass of the Sun. It spins furiously, thousands of times per second, its equator bulging outward from centrifugal force. It is hotter than the core of a supernova, hundreds of billions of degrees, and it is on the verge of collapse. This is not a star, not anymore. It is a supermassive neutron star, a temporary, unstable state of matter held up only by its rapid rotation and thermal pressure. For a brief moment, anywhere from a few milliseconds to a few hundred milliseconds, it resists the inevitable. But the forces at play are too great. The core is so dense that neutrons may begin to dissolve into their constituent quarks, forming a soup of strange matter. Magnetic fields, already trillions of times stronger than Earth's, are twisted and amplified by the differential rotation, reaching intensities we can barely model, and then collapse. In a flash, the core gives way. No explosion, no flash of light, just silence. A point in space where gravity wins. The event horizon forms. A black hole is born. But the story doesn't end there, not even close. Because while the center collapses into darkness, the outer layers of the merging stars are flung outward in a violent explosion. This is the birth of the Kilonova. Not from the black hole itself, but from the wreckage of the collision. As the stars merged, a vast amount of neutron-rich material was torn away, about 1 to 5% of a solar mass, or roughly the mass of Jupiter. This material doesn't escape cleanly. It's not like a rocket launching into space. Instead, it's thrown out in multiple forms, some as a wide, slow-moving tidal tail, some as a faster, more focused outflow driven by pressure and neutrino heating, and some as a swirling disk of superheated plasma that forms around the newborn black hole. This is the accretion disk, a donut-shaped structure of matter orbiting the black hole at nearly light speed. It is incredibly hot, dense, and turbulent. Temperatures exceed 1 billion degrees. The disk glows in X-rays and gamma rays. Viscous forces and magnetic instabilities churn the material, causing it to spiral inward. As it falls toward the event horizon, it releases enormous amounts of energy, more than the sun emits in a year, released in seconds. This energy powers some of the most dramatic features of the kilonova. But the disk isn't just feeding the black hole, it's also launching material. Intense magnetic fields, twisted by the black hole's spin, act like a cosmic slingshot, accelerating particles along the rotational axis. This forms a relativistic jet, a narrow beam of plasma moving at 99.9%, the speed of light. If this jet is pointed even slightly toward Earth, we detect it as a short gamma-ray burst, lasting just a couple of seconds. The jet punches through the surrounding debris, creating a shockwave that heats the material and produces afterglow radiation in X-rays and radio waves, detected days or weeks later. Meanwhile, the slower-moving ejector, flung out in all directions, begins to expand into space. This is the material that will create the kilonova's visible glow. It's rich in free neutrons, hot and expanding at 10 to 30% the speed of light. As it cools, the R process begins in earnest. Neutrons rapidly bombard atomic nuclei, building up heavier and heavier elements: silver, iodine, gold, platinum, uranium. The process is so fast that it bypasses the usual decay chains. In seconds, the periodic table is extended beyond what normal stars can produce. But here's the key. This ejector is radioactive. The newly formed heavy elements are unstable. They decay, releasing energy in the form of heat and light. This is what makes the Kilonova shine. Not from fusion, not from gravitational collapse, but from the glow of radioactive decay, like a dying ember, but one that burns with the light of 1,000 suns. The first light is blue, dominated by lighter R-process elements like strontium and silver, which decay quickly. This phase lasts only a few hours. Then, as the ejector expands and cools, heavier elements take over. The glow shifts to red and infrared, powered by the decay of isotopes like cerium and tellurium. The brightness peaks within a day, then slowly fades over weeks. This is the signature astronomers saw in GW70817. The telltale color evolution that confirmed the presence of heavy elements. But the physics of the collision is far more complex than a simple merger and explosion. Simulations show that the outcome depends critically on the masses of the neutron stars, their equation of state, and their spins. If both stars are relatively light, the merger might form a stable neutron star that survives for seconds or even minutes before collapsing. If one is much heavier, the collapse is nearly instantaneous. If the stars are spinning rapidly, the accretion disk can be more massive, producing more ejecta and a brighter kilonova. And in some cases, the merger might not form a black hole at all, at least not right away. If the total mass is below a certain threshold, the remnant could be a hypermassive neutron star that survives for several hundred milliseconds, supported by differential rotation and thermal pressure. During this time, it can emit powerful gravitational waves, neutrinos, and electromagnetic radiation. Some models suggest that such a remnant could power a longer-lasting kilonova, or even generate a strong magnetic field that influences the jet structure. There's also the question of how much matter is ejected. Estimates from GW7Cu817 suggest between 0.01 and 0.5 solar masses, enough to produce several Earth masses of gold alone. But this material doesn't all escape. Some falls back onto the accretion disk, prolonging its activity. Some is swallowed by the black hole. Only a fraction, perhaps 10 to 20%, escapes entirely, becoming part of the interstellar medium. And yet, that fraction is enough. Because over billions of years, these events accumulate. Every kilonova enriches the galaxy with heavy elements. The gold from one collision mixes with the dust and gas of the Milky Way. It becomes part of molecular clouds. When new stars form, that gold is incorporated into planets, asteroids, comets. Some of it ends up on Earth, brought by meteorites, concentrated by geological processes mined by humans. But back to the moment of collision. What does it look like? We can't see it directly. The event is too distant, too fast, too obscured by debris. But through simulations, supercomputer models that solve Einstein's equations of general relativity, combined with nuclear physics and magnetohydrodynamics, we can visualize it. Picture this: two dense spheres spiraling inward, a flash of contact, a burst of gravitational waves. Then, a violent splash of neutron-rich matter flung outward in spiraling arms. At the center, a bright, pulsating core, spinning, glowing, distorting space. Around it, a glowing disk of plasma, threaded with magnetic fields like golden veins. From the poles, twin jets of energy pierce the darkness, drilling through the expanding debris. The whole system radiates in every wavelength: gamma rays, X-rays, ultraviolet, visible light, infrared, radio. It is chaos. It is beauty. It is the universe remaking itself, and all of this happens in less than a second. After the merger, the black hole settles into stillness. The jets fade. The accretion disk is consumed. The ejector expands into space, cooling, thinning, becoming part of the galaxy's fabric. The gravitational waves stop. The gamma rays vanish. The visible light dims. Within weeks, the kilonova is gone. Just a faint, expanding cloud of gas, invisible to all but the most sensitive telescopes. But the elements remain. The gold, the platinum, the uranium. They are now part of the cosmos, drifting, waiting. For millions of years, they travel through interstellar space. They may be caught in the gravity of a forming star. They may become part of a rocky planet. They may end up in the hand of a human being, shaped into a ring, a coin, a work of art, all from a collision that lasted less than a second. This is the power of the kilonova, not in its duration, not in its visibility, but in its consequence. In its ability to transform two dead stars into the building blocks of civilizations, to turn destruction into creation, to make gold from gravity. But the story isn't over. The collision is just the beginning. The real journey, the journey of the gold, has only just started, because now we must follow that gold. from the wreckage of the Kilonova through the galaxy, across time, until it reaches us. Until it sits on your finger, or in a vault, or in the circuits of a satellite orbiting Earth. That journey from explosion to existence is what we'll explore next. Because the universe doesn't just make gold, it delivers it. There is a moment just after the collision when the universe holds its breath. The black hole has formed, the jets have fired, the gravitational waves have faded into silence. And now, spreading outward from the heart of the explosion, a cloud of debris expands into the void. It is not fire, not in the way we know it. No oxygen, no flame, no spark. But it glows with a strange silvery light, shifting from blue to red, pulsing with a slow radioactive heartbeat. This is the Kilonova's afterglow. And within this glowing cloud, something ancient and miraculous is happening. Atoms are being born. Not just any atoms, not hydrogen, not helium, not even carbon or oxygen, the building blocks of life. These are the heavy elements, the rare ones, the ones that shimmer, the ones that weigh more than lead, the ones that, in a quiet twist of fate, would one day become jewelry, currency, symbols of love and power. This is where gold is made, not in the calm fusion of a star's core, not in the slow decay of ancient rocks, but in the violent, neutron-soaked wreckage of two dead stars. This process has a name, the R process, the rapid neutron capture process, and it is one of the most extraordinary acts of alchemy the universe has ever performed. To understand it, we have to go deeper than chemistry, deeper than planets, deeper than stars. We have to go to the nucleus, to the heart of the atom. Every atom is made of a nucleus, protons and neutrons bound together, surrounded by a cloud of electrons. The number of protons defines the element. 1 proton is hydrogen, 6 is carbon, 79 is gold. But neutrons? They're the silent partners. They don't change the identity of the element, but they stabilize the nucleus. Add too few, and the nucleus falls apart. Add too many, and it becomes unstable, radioactive, prone to decay. Now, in normal stars, elements are built slowly. Hydrogen fuses into helium, helium into carbon, carbon into oxygen, neon, magnesium, step by step up to iron. But iron is a dead end. Fusing iron absorbs energy instead of releasing it. So stars stop there. They can't make heavier elements through fusion. They don't have the conditions. Not enough neutrons. Not enough pressure, not enough speed. But a kilonova? A kilonova is different. In the seconds after the neutron-star merger, the ejected material is a flood of free neutrons, billions upon billions, moving at incredible speeds. The density is so high, the neutron flux so intense, that atomic nuclei are bombarded from all sides. And they don't have time to decay. There's no pause, no rest, just capture after capture after capture. Imagine a tiny nucleus, say iron 56, with 26 protons and 30 neutrons. In the chaos of the kilonova ejector, it's suddenly hit by a neutron. It becomes iron 57. Then another neutron hits, iron 58. Then iron 59. And so on. But soon it's no longer iron. The nucleus is so overloaded with neutrons that it becomes unstable. A neutron spontaneously turns into a proton, emitting an electron and an antineutrino. This is beta decay. And when that happens, the atom changes. Iron becomes cobalt. Cobalt becomes nickel. Nickel becomes copper. Copper becomes zinc, and the process continues, up, the periodic table. But it doesn't stop there. In the Kilonova, The neutron flux is so extreme that nuclei can capture dozens of neutrons before they have time to decay. They become neutron-rich isotopes, so heavy they shouldn't exist. They are like overinflated balloons stretched to the edge of stability, and then decay rapidly, one after another. Protons increase, the atomic number rises, and suddenly element 79, gold. Yes, gold. Not imagined, not dreamed, forged. In less than 10 seconds, from simple iron seeds, the R process builds elements all the way to uranium, plutonium, and beyond. It doesn't happen in a lab. It doesn't happen in a star. It only happens in places where the neutron density is at least 1 billion trillion per cubic centimeter conditions. So extreme, they exist in only 2 places in the universe: the core of a supernova and the debris of a neutron star merger. And here's the stunning part: Kilonovae are better at it. Simulations and observations now show that neutron star mergers produce more heavy elements, faster and in cleaner environments than supernovae. The ejecta is richer in neutrons. The temperatures are higher. The expansion is just right, fast enough to prevent the nuclei from breaking apart, slow enough to allow the R process to run its course. In fact, scientists now believe that most of the gold in the universe, possibly all of it, comes from Kilonovae, not from dying stars, not from stellar winds, not from planetary collisions. From this, the merger of 2 neutron stars. A single event like GW 700117 could have produced enough gold to outweigh our entire planet several times over. And that gold didn't vanish. It was flung into space, destined to drift, to mix, to become part of future worlds. But how do we know this? Because light tells stories. Every element emits and absorbs light at specific wavelengths, its unique fingerprint. When astronomers pointed telescopes at the Kilonova in NGC 4993, they didn't just see a bright spot. They saw a spectrum, a rainbow of light broken into its components. And in that spectrum, they found the unmistakable signatures of heavy elements. Strontium. First, detected in the blue light within hours. Then lanthanides, rare earth elements like cerium and neodymium revealed in the infrared glow. These elements are only produced in the R process. Their presence was the smoking gun. The universe wasn't just hinting at heavy element creation, it was showing us. And gold. Gold doesn't have strong spectral lines in the visible range. It's hard to detect directly, but its presence is implied. You can't make platinum, uranium, or iridium without making gold. They're all part of the same R process chain. The conditions that produce one produce the others. And the total mass of heavy elements observed matches the predictions for gold production perfectly. So while we may not have seen the gold with our telescopes, we know it's there. Like a ghost in the machine, we detect it by its influence, by the weight of its absence, by the glow of its radioactive cousins. Now, imagine being inside that expanding cloud. Not as a human, no one could survive, but as a single atom, a proton, a neutron. You're part of the tidal tail flung from the collision at 20% the speed of light. Around you, space is thick with particles. Neutrons fly past like bullets. Nuclei collide, merge, split. The temperature is 100 billion degrees. The pressure is beyond comprehension. And yet, within this chaos, order emerges. You, a free neutron, are captured by a passing nucleus. You don't last long. In minutes, you decay into a proton, boosting the atom one step up the periodic table. Another neutron hits, another decay, another jump. The nucleus grows heavier. It becomes palladium, then silver, then cadmium, then indium, then tin, then antimony, then tellurium, then iodine, then xenon, then barium, and then platinum, and then gold. For a brief moment, you are part of an atom of gold 197, the only stable isotope of gold. You are no longer radioactive. You are eternal. You will not decay. You will outlast stars. You will drift through space, cooling, joining dust grains, becoming part of a molecular cloud. Millions of years later, that cloud collapses. A new star ignites. Planets form. One of them is rocky. Iron sinks to the core. Silicates form a mantle. Water collects on the surface. Life begins. And deep underground, your gold atom, along with trillions of others, condenses into a vein of pure metal. Eons pass. Volcanoes rise. Mountains erode. Rivers carry sediment. And one day, a human picks up a shiny rock from a stream D. They don't know its history. They don't know it was forged in a collision 30 million light years away. They don't know it traveled across galaxies. They just know it's beautiful. They call it gold. This is not poetry. This is physics. This is fact. And it changes everything. Because for most of human history, gold was magic. Divine, eternal. The Egyptians called it the flesh of the gods. The alchemists believed it was the perfect metal, the goal of all transformation. And in a way, they were right. Gold is perfect, not because it's unchanging, but because it's the product of the most extreme transformation the universe can perform. It is star-made, not from one star, but from the collision of two. From the death of giants, from the birth of black holes, from the fire of neutron-rich chaos. And it's not alone. Alongside gold, the R process creates platinum, used in catalytic converters, medical devices, jewelry. Iridium used in spark plugs and cancer treatment. Uranium powering reactors, shaping history. Silver conducting electricity, reflecting light. Cesium driving atomic clocks, defining time itself. These are not just elements. They are tools. They are technologies. They are civilization. Without Kilonovae, the periodic table would be incomplete. Without heavy elements, Earth would be a simpler world. Rock, iron, silicates, water. No electronics, no chemistry beyond the basics. No possibility of complex life, no way to build machines, no way to measure time with precision. The universe would be poorer in every sense. And yet, this process is rare. Neutron star mergers happen only once every 10,000 to 100,000 years in a galaxy like ours. They are fleeting, they are distant, but over billions of years, their cumulative effect is profound. The gold in Earth's crust, about 2.5 billion metric tons, likely came from just a few dozen such collisions scattered across cosmic time. Each one a cosmic foundry, each one a gift to the future. So the next time you see gold on a finger, in a museum, in a circuit board, don't just see a metal, see a story. See two stars that lived, died, and collided. See a flash of gamma rays. See a ripple in space-time. See a cloud of radioactive debris glowing in the dark. See the R process in action. Neutrons flying, nuclei growing, atoms transforming. See the universe creating. Because gold is not just a symbol of wealth. It is a symbol of cosmic violence turned to beauty, of destruction becoming legacy, of two dead stars giving life to something eternal. And this alchemy of the cosmos is only possible because the universe is not just vast, it is creative. It does not just destroy, it transforms. But the journey isn't over. The gold has been made, but it must travel. It must survive. It must find its way to a planet, to a species, to a moment when a human being decides to shape it into something meaningful. That journey from space to skin is what we'll follow next. Because the story of gold doesn't end in the stars, it begins there, and then it comes home. The explosion is over. The light has faded. The jets have pierced the dark and vanished. The black hole sits silently at the center, feeding on the last remnants of the accretion disk. The gravitational waves have rippled outward and dissolved into the fabric of space-time. To the universe, it's as if nothing happened, just another brief flicker in the endless night of space. But something did happen, something irreversible, something eternal. Because scattered across the void, carried by the expanding fireball, is a cloud of stardust rich with gold, platinum, uranium, and 100 other rare elements. This is the ashes of the Kilonova. Not literal ash, not charcoal or soot, but atomic debris, microscopic grains, atoms, ions, hurtling through interstellar space at thousands of kilometers per second. And though the explosion is finished, the journey has only just begun. This is not the end. It is a beginning. The ejector, weighing as much as Jupiter, spreads outward in an ever-growing sphere. At first, it's hot, glowing with the energy of radioactive decay. But as it expands, it cools. The gas thins. Atoms collide, bond, form molecules. Gold atoms, once part of a chaotic plasma, begin to clump together. They don't form nuggets, not yet. But in the cold of space, they stick to dust grains, coating them like frost on a window pane. These grains are no bigger than specks of pollen, but they carry within them the legacy of a cosmic collision. And now they drift. Not aimlessly, not randomly. They are caught in the great currents of the galaxy, the slow, majestic flow of gas and dust that circles the Milky Way. This material joins the interstellar medium, the thin soup of hydrogen, helium, and trace elements that fills the space between stars. It mingles with gas clouds, spiral arms, magnetic fields. It is pushed by stellar winds, pulled by gravity, shaped by shock waves from other supernovae. Over time, thousands, then millions of years, the debris slows. It loses energy. It becomes part of a cold, dense molecular cloud, giant regions of gas where new stars are born. These clouds are vast hundreds of light years across, weighing tens of thousands of times the mass of the Sun. They are dark, opaque, lit only by the occasional newborn star. Inside them, gravity begins to work. Tiny fluctuations in density grow, regions collapse, filaments form. And within one such filament, perhaps 100 million years after the Kilonova, something stirs. A knot of gas, enriched with the heavy elements from the neutron star merger, begins to contract under its own gravity. It spins, it heats up. At its center, pressure builds, temperature rises. And then, ignition. A new star is born. This is not our Sun, not yet. But it could have been. Because this is how all stars form, from the wreckage of the old, from the ashes of the dead. The Sun itself was born this way, about 4.6 billion years ago, from a molecular cloud seeded with heavy elements from countless supernovae and kilonovae that came before it. That cloud collapsed, spun, flattened into a disk. At the center, the Sun ignited. Around it, the disk cooled. Dust grains collided, stuck together, grew. And in that disk, where temperatures varied from scorching near the star to frozen at the edges, the gold from the Kilonova played its part. Close to the young Sun, it was too hot for ice, but not for metal. Iron, nickel, gold, platinum. These refractory elements condensed into solid grains. They clumped into pebbles, then boulders, then planetesimals, rocky bodies hundreds of kilometers wide. Some collided, merged, grew. Over millions of years, they became planets. Earth was one of them. But gold didn't stay evenly distributed. During Earth's formation, the planet was molten, a global magma ocean. Heavy elements like gold and platinum, being dense, sank toward the core, pulled by gravity. Scientists estimate that over 99% of Earth's gold is locked in the core, forever out of reach. It's not gone. It's just buried. 6,000 kilometers beneath our feet, swirling with liquid iron in temperatures hotter than the surface of the sun. So why is there any gold on the surface? Because of a second cosmic delivery. Long after Earth had cooled and solidified, the solar system was still chaotic. Asteroids, comets, and planetesimals remained. And for about 500 million years, Earth was bombarded by impacts, a period known as the Late Heavy Bombardment. These weren't just random rocks. Many were fragments of shattered protoplanets, rich in metals. And when they struck Earth, they didn't just leave craters. They delivered new heavy elements, gold, platinum, iridium deposited into the crust and mantle. This is where most of the gold we mine today comes from, not from Earth's original formation, but from asteroid impacts. And those asteroids? They were likely born in the same primordial disk, enriched by the same Kilonovae that seeded the solar system. So, every piece of gold on Earth has a dual origin, forged in a neutron star collision hundreds of millions or even billions of years before the sun existed then. Delivered to our planet by asteroid impacts after it formed. It is twice extraterrestrial. It is cosmic in the truest sense. And once it was here, it stayed. Gold doesn't rust, doesn't oxidize, doesn't react with most chemicals. It is chemically inert. It survives erosion, volcanism, plate tectonics. Over billions of years, geological processes concentrated it into veins, brought it closer to the surface, made it accessible. Hydrothermal fluids, heated by magma, dissolved gold from deep rock and redeposited it in quartz fractures. Rivers eroded mountains, carried gold particles downstream, concentrated them in riverbeds. Miners would later follow these trails, unaware that they were tracing the path of a collision that happened long before time began. But the journey didn't end with geology. It continued into culture. The first humans to find gold didn't know its origin. They didn't need to. They saw its luster, its weight, its resistance to change. It didn't tarnish like copper. It didn't break like stone. It could be shaped, yet it held its form. It reflected light like no other metal. To early civilizations, it seemed magical, divine. The Egyptians buried their pharaohs with golden masks, believing it was the skin of the gods. The Incas called it the sweat of the sun. The Greeks associated it with Apollo, the god of light. It became a symbol of immortality, purity, power. Kings wore it. Empires fought for it. It drove exploration. The Spanish conquest of the Americas, the California gold rush, the scramble for Africa, and eventually it became money. Not because it was useful. Gold is too soft for tools, too rare for widespread use. But because it was trusted, it was scarce, it was durable, it was beautiful. It became the universal standard of value, the anchor of economies, the reserve in vaults, the silent witness to human ambition. But even as gold shaped civilizations, its cosmic origin remained hidden. Not until the 20th century did we understand nuclear fusion. Not until the 21st did we witness a kilonova. And only now do we realize every ounce of gold ever held, traded, worshipped, or worn was born in a collision of dead stars. Think of that. The gold in a Roman coin, the gold in a Victorian crown, the gold in a modern wedding ring, the gold in a satellite orbiting Earth, the gold in the connectors of your phone, all of it traces of a fireball 130 million light years away. All of it stardust from a moment of cosmic violence. And it's still happening. Right now, somewhere in the universe, two neutron stars are spiraling toward each other. Maybe in a distant galaxy. Maybe in our own Milky Way. They're emitting gravitational waves, tightening their orbit, racing toward collision. In a few million years, or perhaps tomorrow, they will merge. There will be a flash, a burst of gamma rays, a kilonova, and a new cloud of gold will be born, flung into space, beginning its long journey towards some future world. We may never see it, but it's happening. And when it does, the universe will once again perform its greatest alchemy, turning destruction into beauty, chaos into treasure, star death into human wonder. But the story still isn't over. Because gold is not just out there. It's in here, in our hands, in our history, in our blood. Because the elements forged in Kilonovae aren't just in jewelry and vaults, they're in our bodies, in our technology, in the very fabric of life. That's where we're going next. Because the legacy of the Kilonova isn't just gold, it's us. Look at your hand, hold it up, turn it in the light. If you're wearing a ring, especially one made of gold, look at it closely. See how it glimmers, how it catches the light and holds it like a captured star. That gold wasn't dug from the earth. Not really. It was delivered to Earth, forged in a fire 130 million years ago, in a collision so violent it shook the fabric of space-time. It traveled across galaxies, survived supernovae, rode asteroid impacts, endured eons of geology, and now it rests on your finger, a tiny shining relic of the most extreme event in the universe. And it's not alone, because gold is not the only element in your life that came from the stars. It's not even the most important. The iron in your blood, the calcium in your bones, the oxygen you breathe, the carbon that forms the backbone of every molecule in your body, these were all forged in the hearts of stars. But the heavy elements, the rare ones, the ones that make life not just possible, but complex, those came from events like Kilonovae, iodine, essential for your thyroid, selenium, a powerful antioxidant, tellurium, used in solar cells, platinum, used in chemotherapy, even the uranium that powers reactors and shapes history. These are not byproducts of ordinary stars. They are gifts from cosmic collisions. Without Kilonovae, the periodic table would be incomplete. Without them, the chemistry of life would be simpler, slower, less diverse. And gold? Gold may not be biologically essential, but it is culturally profound. It has shaped human history. It has funded empires. It has inspired art, war, exploration, and love. It is the metal of choice for wedding rings, not because it's useful, but because it endures. It doesn't tarnish. It doesn't fade. It symbolizes something eternal. And in a way, it is eternal. Because the atoms in that ring are older than Earth, older than life, older than time as we understand it. Every atom of gold in your possession was created in a neutron star merger, and every one of those atoms has been conserved since then. Atoms don't die. They don't vanish. They only transform. The gold in your ring could have once been part of a meteorite that crashed into ancient oceans. It could have been worn by a pharaoh, melted down by a Roman emperor, carried across continents by a prospector. It has no memory, but it has history. A history written in gravity, in fire, in time. And so do you. Because you are not just made of stardust, you are made of kilonova dust, of neutron star ash, of gold born in a collision. Your body contains trace amounts of heavy elements, some of which likely came from our process events, like the one we've been exploring. The very complexity of your DNA, the precision of your cells, the conductivity of your nerves, these depend on a rich, diverse chemistry, and that chemistry was seeded by explosions in deep space. You are not separate from the cosmos. You are part of it. Not metaphorically, literally. When you look up at the night sky, you are not just observing distant stars, you are recognizing them. You are seeing the ancestors of your atoms, the furnaces that cooked the elements in your blood, the collisions that forged the metals in your world. The universe isn't out there. It's in here, in your hands, in your heart, in your mind. And that changes everything, because for most of human history, we saw ourselves as separate from nature, as masters of the earth, as exceptions to the rules. But science has revealed a different truth. We are connected, not just to life on Earth, not just to our planet, but to the entire cosmos. We are the universe becoming aware of itself. We are stardust that learned to think, to feel, to wonder. And the Kilonova, this brief, violent, beautiful event, is one of the key chapters in that story. It's easy to think of the universe as cold, distant, indifferent. And in many ways, it is. Stars explode, planets die, galaxies collide. Life is rare, but within that vastness, there is creation, there is beauty, there is meaning, not imposed from outside, but emergent, born from the laws of physics, from the dance of atoms, from the slow accumulation of complexity. A kilonova doesn't care that gold will one day be worn as a symbol of love. It doesn't know that platinum will treat cancer. It doesn't plan for uranium to power cities. And yet, those things happen, because the universe, in its blind, mechanical unfolding, produces the conditions for possibility, for life, for intelligence, for art, for connection. And now, because of science, we can understand it. We can stand on a planet orbiting an ordinary star in an ordinary galaxy and know where gold comes from. We can detect ripples in space-time. We can decode the light of distant explosions. We can trace the journey of an atom from a neutron star merger to a human hand. That is not just knowledge, that is power. The power to see the universe not as a mystery, but as a story, one we are now part of telling. So the next time you see gold, whether in jewelry, in a museum, or in the circuitry of a device, don't just see a metal, see a cosmic journey. See two stars that lived and died. See a flash of light across 130 million light years. See a cloud of dust drifting through space. See an asteroid striking a young Earth. See a miner digging deep into rock. See a craftsman shaping it into something beautiful. See the entirety of time, because that gold has survived longer than mountains, longer than oceans, longer than species. It has outlasted empires. It will outlast civilizations. And one day, when humans are gone, that gold will still exist, perhaps buried in the crust, perhaps scattered in space, perhaps orbiting a distant star. And if another intelligent species finds it, they may wonder, where did this come from? And if they're lucky, they'll have the tools to find out. They'll look to the sky. They'll detect gravitational waves. They'll observe a kilonova. They'll understand, and the story will continue. But for now, the story is ours. We are the first species, so far as we know, to understand our cosmic origins, to trace the path from neutron stars to necklaces, from black holes to biology, from the Big Bang to the present. And that understanding is not just for scientists, it's for everyone. Because wonder is not a luxury, it's a necessity. It's what drives us to explore, to ask questions, to build telescopes, to launch satellites, to write stories, to make art. It's what makes us human. So look up, not just with your eyes, but with your imagination. See the darkness between the stars. That's not emptiness. That's where the next kilonova is forming, where two neutron stars are spiraling toward their final embrace, where gold is being born, even now, in silence and fire. And when it happens, when the next one flashes across the sky, we'll be ready. We'll have our telescopes, our detectors, our minds open, and we'll watch, not as strangers, but as family. Because we are all children of the same universe, we are all made of the same stuff, and we are all in our own way glowing with the light of dead stars. So the next time you hold a piece of gold, don't just hold it, honor it. Honor the stars that died too. Make it. Honor the universe that created the conditions for life. Honor the curiosity that allowed us to discover its story. And honor the future, where others may look up and wonder, just as we do. Because the cosmos is not just our origin, it is our home. And the story of the kilonova, the story of how gold was born in a cosmic collision, is not just a tale of physics, it is a love letter from the universe to us. So go ahead, wear that ring, hold that coin, touch that metal, and know you are touching the ashes of stars. You are wearing the fire of creation. You are, quite literally, golden. Now go out there, look up, and never stop wondering, because the universe is still writing its story, and you're part of it.